Every day in India, millions of digital microtransactions flow through the UPI network. A phone scans a vendor's code, a cryptographic handshake occurs, and a bank balance updates thousands of miles away in a fraction of a second. The same intensity applies to the IRCTC Totcall booking system. At 10 a.m. sharp, millions of users simultaneously hammer the servers, fighting for a finite number of available train tickets. At the physical center of these massive digital bottlenecks is the CPU. Inside those silicon chips, execution units are processing billions of mathematical operations every single second to keep those national systems from crashing. But there is a severe mathematical discrepancy in how this hardware evolved. For decades, processor clock speeds increased by about 50% annually. During that same period, the physical RAM modules that feed those processors improved their access speeds by only 7% a year. The processor executes instructions with the raw speed of a hypercar, but its data delivery mechanism supplies memory at the pace of a bullet cart. This growing gap is known as the memory wall. A modern processor operating at 3 GHz can execute a calculation in less than a third of a nanosecond. If it has to wait 80 nanoseconds for main memory to retrieve the next piece of data, that CPU spends over 99% of its operational life completely idle. To keep global computing from grinding to a halt, hardware engineers couldn't rely on physics to yield suddenly faster RAM. They had to construct an entirely new way to manage data. This diagram shows the architectural solution to that latency gap, the memory hierarchy. The structure is governed by a strict physical trade-off. Faster memory technologies cost significantly more to manufacture, meaning systems can only afford to install very small amounts of them at the top. At the base of the hierarchy, you find tertiary storage like optical disks and magnetic tape. These materials can hold massive archives of historical data for pennies per gigabyte, but retrieving that data might take several minutes. This block diagram breaks down the top end of the hierarchy, where the speed problem is actually solved. Between the main RAM and the CPU core sits cache memory, a high-speed buffer built from highly responsive static RAM. Modern processors divide this buffer into 3 tiers. Level 1 is tiny, just tens of kilobytes, and built directly into individual CPU cores for instant access. Level 2 provides a medium-sized fallback, while Level 3 is a larger pool shared across all the cores on the processor. The system continuously shuffles data up and down this ladder. By keeping the most actively used data at the very top, the computer achieves maximum processing speed without inflating the total cost of the machine. This flowchart maps the decision logic that executes every time the CPU needs a new piece of data. First, the controller checks the local cache. If the data is already there, it's called a cache hit. The information is fed to the processor in under 4 nanoseconds. If the data is missing, the system suffers a cache miss. The processor is forced to halt execution and fetch the information from the slow main memory, paying a massive latency penalty. Computer architects measure the success of this system using this equation, effective access time. It balances the fast cache retrievals against the slow memory penalties to calculate the actual average speed of the system. If a processor hits the cache 95% of the time at 4 nanoseconds, and only misses 5% of the time with an 80 nanosecond RAM delay, the effective access time averages out to just 7.8 nanoseconds. Because modern hardware achieves hit rates between 90 and 99%, the CPU successfully bypasses the devastating RAM delay for nearly every instruction it runs. This raises an engineering puzzle. How does a blind piece of silicon predict exactly what data the CPU will ask for next and get it right 95% of the time? The hardware relies on a behavioral pattern called the principle of locality. It turns out that human-written software doesn't access memory at random. It requests data in highly predictable, localized clusters. This graph visualizes temporal locality. A program accessing a specific memory address is highly likely to ask for it again soon. The right diagram demonstrates spatial locality. When a processor requests data, it assumes it needs adjacent data too, pulling an entire block into cache. This diagram compares cache mapping strategies. Most processors use set associative mapping on the far right. It provides optimal balance, ensuring data is found quickly without constantly overwriting important files competing for the exact same memory slot. The cache controller doesn't possess foresight. It simply exploits the fact that software code naturally runs in tight, repetitive loops and grabs the surrounding data before the CPU even realizes it needs it. For software developers, understanding this physical hardware layer dictates how to write code that actually performs at scale. Look at these two identical algorithms reading a two-dimensional array of numbers. One iterates through the grid row by row. The other jumps down column by column. The math is identical, yet the row-by-row code executes up to 100 times faster. By moving linearly across the memory addresses, it honors spatial locality, allowing the hardware to feed it from the fast L1 cache instead of constantly waiting for fresh blocks from main RAM. This level of optimization sustains massive national databases. When Aadhaar servers verify millions of biometric fingerprints against a central registry, the system relies entirely on large, shared L3 caches to push that identity data across dozens of processor cores simultaneously without choking the system bus. On the National Stock Exchange, high-frequency trading algorithms depend on a hardware feature called a write-back policy. Instead of executing thousands of slow individual trade rates directly to main memory, the cache batches the modifications locally, writing them to RAM in single bursts to maintain sub-millisecond execution speeds. The memory hierarchy operates as a masterfully engineered illusion. By layering progressively faster silicon, the architecture tricks the processor into acting as if connected to a memory drive as vast as the cloud, but as responsive as an on-chip register. For anyone engineering at scale, the physical rule remains absolute. Memory is the bottleneck. Cache is the solution.